Okay, it's a little bit of a giveaway when in a picture it has theta dot, theta, and r. But in general, even if those weren't on the picture, whenever you see a straight arm rotating around a pivot and there's some kind of collar or pin that's riding along that straight arm, that lends itself to r theta because the straight rod rotating around will be theta, and the pin sliding along the rod or the collar sliding along the rod, that will be r. So this is definitely an r theta problem. And so what we need to do is find the force of the rod on the particle and the force of the slot on the particle, and that would be hard to do if both sides of the slot were pressing on the pin. And so it's saying that the slot can only press on either the left side or the right side. And so we just have to guess that force being left or right, and if we get a negative sign, it means the other side was pushing on it. Okay, and so let's start with the free body diagram of the little pin. So I'm going to draw a tiny little loop right around the pin. There we go. And so we need to draw what's in the little red loop there. I'm going to try and draw a circle as best I can. Okay, and so the force is on there. Okay, so there is, because the rod is smooth, there is a normal force here, okay, from the rod, okay, and let me just draw in the dot of the rod there, and that's the angle theta, so that's clearly going in theta direction. Okay, so now this is where this little thing about only one side of the slot can be touching. So there is this force here of the slot, and we'll call that from the rod there. Now if both sides could be touching, we would have this extra force in here. We'd have to call one F slot left, F slot right, and that would just get too complicated. So that's what we're going to do. We're going to say that the pin is touching the left side of the slot. If we get a negative for that force, that means the right side's touching. Okay, and so that is the free body diagram. And all you do, if you remember, you just redraw everything here. And I'm going to draw that dotted line there with the theta. And here you put MA. And so this is to remind you, that's the R direction. That's the theta direction or transverse direction. So that means we have mass times A in the radial and mass times A in the theta. Okay, so they want to know what the force of the slot and the force of the rod are. We should be able to solve that if we knew what the accelerations were. And we just finished chapter 12, so let me refresh your memory. A in the R direction, remember, is R double dot, the acceleration along the radius linearly, minus the centripetal acceleration coming back in, R theta dot squared. And so let's see if we know that. They just give us theta dot and theta double dot. We're going to have to get R and R double dot. Before we do that, let's get the other acceleration. A theta, remember, is just the radius times the angular acceleration, theta double dot, which is 0, so that's nice, plus this weird Coriolis 2 r dot theta dot. And remember, one r dot theta dot comes from the r velocity changing, and one comes from the theta velocity increasing because the radius is getting bigger simultaneously. Okay, so we know that theta dot equals 2 radians per second and theta double dot is 0. So we need to know r, r dot, and r double dot. And we're going to have to use geometry. So here we go. There's the triangle we need to know. There's the radius. There's theta. And we are fortunately given that that's 0.5 meters. And we can relate r to theta. We know that r cosine theta equals 0.5 meters. Taking derivatives of both sides using the product rule and the chain rule, we get that r dot cos theta. Okay, so just so you can keep track, that's A, that's B. Okay, so you take the derivative of A times B plus A times the derivative of B. And I paused there because for the life of me, I just can't remember which one has a negative on it, derivative of cosine or derivative of sine. So the derivative of cosine theta is minus sine theta. And then by the chain rule, you have to take the derivative of the theta, so times theta dot. Okay, and so, and if you're keeping track, that's the derivative of B, and that was A. And of course, the derivative of 0.5 is 0. And remember, we're trying to get r dot. And so here we have, we need r and r dot. So sorry, let me slow down. So r is 0.5 over cos theta, and r dot is r sine theta, theta dot all over cos theta. Okay, next is r double dot. And rather than differentiating r dot, I'm going to differentiate this equation right there. So we've done this before using the product rule and the chain rule and all that. I'm not going to explain. I'm just going to do it. Okay, so you can look at previous examples to follow along. So the derivative of r dot cos theta is r double dot cos theta plus r dot derivative of cos theta, I can remember now, is minus sine theta, theta dot, okay, plus the triple product rule. There's three things there, r, sine theta, and theta dot, and I'm going to bring that negative sign out, so it's going to be minus, okay, this whole thing, r dot, sine theta times theta dot plus r times the derivative of sine theta, which is cos theta, and by the chain rule, another theta dot times theta dot, and finally plus r sine theta, theta double dot, but theta double dot is 0. Okay, and that all equals 0. Okay, so expanding this out a little bit, r double dot cos theta minus sine theta r dot theta dot minus sine theta r dot theta dot minus cos theta r theta dot squared equals 0. And finally, r double dot equals sine theta r dot theta dot, two of them, plus cos theta r theta dot squared all over cos theta. There we go. We have everything we need. We're just going to have to plug some things in. I'm going to actually pause and you don't need to see the algebra, and I'll come back when I finished it. Okay, so I spent quite a time with my computer and calculator, and this is what I got. So I got theta dot and theta double dot were given, and then I calculated r dot, and r double dot. You need to be handy with your calculator if you want to be quick with that, and even then it takes quite some time. Okay, and the reason we were doing these things is that we needed to get the radial acceleration and the theta acceleration, which is r double dot minus r theta dot squared, and a theta was r theta double dot plus 2r dot theta dot. And so you plug in the numbers as 3.85 minus 0.577 times 2 squared, and a theta equals r times 0, theta double dot 0 plus 2 times r dot 0.667 times 2. And again, let me pause and run that through my calculator. So that comes out to 1.54 meters per second squared, and that comes out to 2.67 meters per second squared. Okay, so because this recording thing can't scroll up or down very easily, I'm going to go copy the free body diagram and paste it back down here. I'm going to pause again. Okay, so here's that free body diagram that I drew earlier. I'll put that right here. And so what we're going to have to do now is take x and y components, or r and theta components, however we want to do it. And so what I think I'm going to do is I'm going to do r and theta components. And just so we don't get confused, this FR here stands for rod and slot, not radius and theta. Okay, so let's take some forces in the r direction, and also the accelerations in the r direction. And r is positive out that way, and again, theta is 30 degrees. Okay, so we've got F slot cos 30 degrees, okay, because that's theta over there. The rod does not have a component in the r direction because it's normal to the rod, the force from the rod, okay, equals MAR equals the mass was that was so far back, half a kilogram, so 0.5 kilograms, and we just figured out the theta, the r acceleration was 1.54 meters per second squared, and we get that the force in the slot is, and I got the wrong force. And so when I looked at it more carefully, I missed that it said the slot was vertical, which meant up and down, which meant in the direction of gravity. So what I am missing on my free body diagram is this, the weight of the pin, and it's half a kilogram times 9.81. So I missed that. So what we have, if you take the radial component, and so that, because it's at 90 degrees, that's theta over there. Let me see if I can figure this out. I'm missing a minus 0.5 times 9.81 sine 30 degrees. So let me write that all out corrected for you. So it is F of the slot cos 30 degrees, and the part that I missed because I didn't have the weight in there because I didn't see that this was not horizontal, it's vertical, so there's weight, minus 0.5 9.81 sine 30 degrees, so that's what I'm missing. So I'm glad I checked before I continued on. 0.5 times 1.54 meters per second squared. That will significantly change it. And so now the force in the slot is 3.72 newtons, which is correct. So now we can continue with, see if we can fit this on the page. Sum F theta is MA theta, and positive is always counterclockwise, which happens to be that way at 60 degrees. Okay, so we get F slot sine 30 degrees. That's going clockwise, so negative. Minus 0.5 times 9.81 cos 30 degrees. The weight is also going clockwise. Plus F of the rod, that is going counterclockwise, equals M, which is A theta, which is 0.5, and the acceleration in the theta direction was 2.67 meters per second squared. And let's continue on to the next page. So the slot we just got as 3.72 newtons. And we'll just write it all out. And so finally, solving for F rod, we get 7.44 newtons, which is correct.